In this video, we're going to talk about Module 1, Topic 1, Lesson 1, and this is Part 2. So if you need to see the first half of the lesson, go watch the previous video. So our essential questions. By the end of both sets of videos, we should be able to answer these two questions. How do you determine where to shade when graphing an inequality? And how do you determine the solution set to a system of inequalities? So moving on to where we left off. First thing, it says the solution of a system of inequalities is the intersection of the solutions to each inequality. Every point in the intersection satisfies all inequalities in the system. So what that means is you're going to graph one inequality shade, you're going to graph a second inequality in shade, and any more. And what you're looking for is that overlapping shading area. So part A says select one ordered pair that represents a point inside the overlapping region. Verify that this is a solution to the system of linear inequalities. So if I go back here, I want to pick a point, any point in here, and I decided to pick 16, 1. Okay, so what we're going to do is we're going to verify that this is a solution. So I'm going to come back here. We're going to write 16, 1, so we know what point we're working with, and we're going to plug it in to all of our inequalities. So we had 10 times 16 plus 7.5 times 1, and that has to be greater than or equal to 90. So we would type this in the calculator. So 10 times 16 plus 7.5 times 1, and that would give us 167.5, and that is greater than or equal to 90, so that works out. So then you check your second equation. That would be 16 plus 1 is less than or equal to 20. That is 17 is less than or equal to 20, and that works out. Now, we did have two other stipulations. Our x's had to be greater than or equal to 0 and our y's. So to double check that, 16 is our x. That is greater than or equal to 0. And 1 is our y. That is also greater than or equal to 0. So this is showing that the point 16, 1 works in all four of our equations. Okay, now the next part, select an ordered pair that represents a point outside the overlapping region. Verify that that is not a solution to the system of linear inequalities. So we can pick any point that we want that's on the outside, so a point over here or a point down here. Since we have a point here already, let's pick something here just to try it. So let's do the point 4. So 2, 4, 2. So right here, let me change my color. So we're going to do that point. That is 4, actually that is 4, 4. So let's do that. Okay. So going back, the point we're working with is 4, 4. So we're going to plug that in to our first inequality, second inequality, and then the previous two as well. So we have 10 times 4 plus 7.5 times 4 needs to be greater than or equal to 90. So we type that into the calculator and we get 70 is greater than or equal to 90. Notice that that is not a true statement. That is false. That is not greater than or equal to. Okay, when we plug it into the second one, we have 4 plus 4 is less than or equal to 20. That would be 8 is less than or equal to 20, and that checks out. And then the second one, our third one, 4 is greater than or equal to 0, and 4 is greater than or equal to 0 for our y's. Those check out. But this is not a solution because it did not work in all four inequalities. We had one inequality that provided a false statement. Okay, So keeping that in mind. So now let's move on to a new example. We're done with Janice and her jobs. Now we're going to talk about Brad. Brad is a distance runner who wants to design the most effective workout plan to prepare for his next race. To adequately prepare for the race, Brad plans to do a combination of running and strength training. He must run between 3 to 6 hours per week, and he wants to devote at least twice as much time to running as to strength training. Brad can spend no more than 8 hours working out each week. So here we go. We need to define our variables. So first thing, let's let X equal the number of hours spent running per week. And Y is the number of hours spent strength training. Okay, per week. So, first things first. It says he must run between 3 to 6 hours per week. So running is our X variable, and so what we're going to do is we're going to put our X variable in between 3 and 6, and that represents between 3 and 6. Okay? Then it says he wants to devote at least twice as much time to running as strength training. Okay? So that means that our running, X, is going to be twice as much or more than 2 times his strength training. Okay. Next, it says Brad can spend no more than 8 hours working out each week. So that would be X plus Y, no more than 8 hours, which means we can't go over 8 hours, so it's going to be less than or equal to 8. Now, because this is a real life situation, we do need to add some constraints, okay? What we need to make sure we add is that Brad cannot work out negative hours or run negative hours, so X has to be greater than 0, and Y has to be greater than or equal to 0 because he cannot strength train negative hours. So what we're going to do is we're going to graph this system of linear inequalities on the coordinate plane, and we're going to shade the overlapping area. So first things first, 3 to 6. What that's going to look like is we're going to have a vertical line at 3 and a vertical line at 6. Okay? What this represents is that he has to work out between run 3 to 6 hours. You're not highlighting yet, but I'm going to show you. This would be the area that's highlighted because that's what's in the middle for that part. Now, the X is greater than or equal to the 2Y. If we want to easily graph this, okay, we can solve for Y, and that puts it in slope-intercept form. So that means I would just divide by 2, and there's technically a 1 there. So I get a 1/2 X is greater than or equal to Y. So that tells me that my Y-intercept is 0 and that my slope is 1/2. So I'm just going to go up 1 over 2. Oh, you got to be careful. Up 1 over 2 because the scaling's different. So up 1 over 2. And I'm just going, I didn't put that in the right spot. So you got to be very, very careful with this. So up 1 over 2, so it should be there. And then if I go up 1 again, over 2, I'm here. So then I'm just going to try to connect the dots as best as possible. And we get that. Now, to figure out our shading here, we can plug in our test point. So if we do a test point for 0, 0. Oh, we can't use 0, 0 this time because our graph went through 0, 0. So what we can use instead is we can use the point 1, 1 to help us out. And so that would be 1/2 times 1 is less than or equal to 1. So that is 1 or greater than or equal to. So 1/2 is greater than or equal to 1. That is false. So here is where 1, 1 falls. So we want to shade the opposite area because that was a false statement. So we would end up shading down here. Again, you're not shading because I'm going to end up erasing. What we're looking for is where do all of these overlap. Okay. The next one is x plus y is less than or equal to 8. So we need to find our intercepts. So to find our x-intercept for that, okay, we plug in 0 for y. So that would be x plus 0 is, we're just going to use an equal sign, equal to 8. So that gives me an x-intercept of 8. When I do my y-intercept, that would mean we plug in 0 for x, and I get y equals 8. So I have 8 as a y-intercept. I have 8 as an x-intercept. I'm going to connect those two dots. Then if I want to figure out where to shade, I do my test point. For this one, I can use 0, 0 because our graph did not go through it. So if I do that for my test point, that would be 0 plus 0 is less than or equal to 8, which is true. So I want to shade the area that contains 0, 0. So that would be below this green line here. Okay. And then lastly, we have our two restrictions that cause us to be in the first quadrant. So x being greater than or equal to 0 would be here. And that would allow me to shade all of this area. And then y being greater than or equal to 0 would be here. And I would shade all above that. So what we're looking for are where does all the overlapping shading area happen? Okay, where does it all overlap? It all overlaps in just this little piece right here. So I'm going to erase all my highlighting and I'm just going to focus on highlighting this piece right here, and that's all you should highlight on your paper. Okay, so let me get rid of it. And all we care about is this piece right here because that's where all the shading ended up overlapping. This little piece works in all 5 of our inequalities. Okay. So next part, you can use the intersection points to determine optimal solutions to a system of inequalities through the process called linear programming. Okay, in linear programming, the vertices of the solution region of the system of linear inequalities are substituted in to a given equation to determine the maximum or minimum value. So what we want to do for part A is we want to label the vertices in the shaded region. So the vertices are our corners. So we have one right here at 3, 0. We have one right here at 1/2, or sorry, 3, 1/2. 1.5, yeah. So 3, 1.5. This one right here is at about 5.333, 2.667. Here is at 6, 2. And this last one is at 6, 0. Okay, so that was that one. Now, it says running burns 600 calories per hour while strength training burns 250 calories per hour. Write an equation to represent this relationship. Be sure to define your variables. So we still have the same variables where X is the number of hours running. Y is the number of hours strength training. And now we didn't get what we're setting this equal to, so we're going to say W is total calories burned. So if he burns 600 calories strength training, that's going to go with the Y. And if he burns 600 calories running, so that's going to go with the X. 600 calories running plus 250 calories strength training. That's going to be equal to our total calories burned, which is W. So now what we want to do is we want to use the vertices of the solution to determine how many hours Brad should devote to each type of exercise in order to maximize the number of calories burned. So what we're going to do is we're going to take that equation and we're going to plug in all 5 of those vertices. So we're going to have this 5 different times. Oh, there were 6 vertices, so 6 different times. So here we go. We have 600 times 3 plus 250 times 0. So type that into your calculator, get a number. You should get 1,800. And if you need to pause so you can use the calculator, please do that. Then we had 600 times 3 plus 250 times 1.5. Plug that into your calculator. You should get 2175. Then we have 600 times 5.333 plus 250 times 2.667. When you type that into your calculator, you should get 3866.55. Then we have 600 times 6 plus 250 times 2. That gives us 4,100. And then we have 600 times 6 plus 250 times 0. And that gives us 3,600. So all we did again is we took these points right here, 1, 2, 3, 4, 5. Okay. And we plugged them in. Okay. And so what we're looking for is which one is going to maximize the calories burned. So which one of these numbers is the maximum, the greatest value? That would be this one right here. So what that tells us is that Brad should devote 6 hours to running and 2 hours to strength training. To maximize the number of calories burned. Okay, so again, all you did is you plugged in those vertices because those are the extreme points of the graph. Okay, so we're going to keep on moving. This is the last question. So, a sponsor wants Brad to advertise their company by wearing its brand name on his workout gear. They will pay him $15 for each hour he wears the brand name while running, and $20 an hour for the brand name while strength training. Determine how many hours Brad should devote to each type of exercise in order to maximize his earnings. So now we have a new equation. He's getting paid $15 per hour he runs, plus $20 per each hour he strength trains, and that's going to be his earnings. So we have a new variable. E is his total earnings. So we're going to do the same concept where we're going to plug in those 5 vertices to see which one maximizes his earnings. So that would be 15 times 3 plus 20 times 0. He would just get $45 from that. If we do 15 times 3 plus 20 times 1.5, he would get $75 for that. If he did 15 times 5.333 plus 20 times it's not 1.5, it's 2.667, he would end up earning $133.34. If he did 6 hours running plus 2 hours strength training, he would get $130. And lastly, if he did 6 hours running but no hours strength training, he would get $90. So we want to know what's going to maximize his earning. That would be if he works out or runs 5.33 hours and strength trains 2.667 hours. So Brad should devote 5.333 hours to running and 2.667 hours to strength training. To maximize his earnings. Okay, so again, we just had to write an equation. We plugged in the vertices. We found which number was the greatest. Okay, so now that we're done, you should be able to answer the following questions in complete sentences. So what is the difference between a solid and a dotted line when graphing, and how do you know when to use each one? How do you determine where to shade when graphing an inequality? And draw an example of a system that would yield no solution. So again, answer those. If you have any questions, please make sure you write them down and you ask me in class.